Hi, in this example, we are going to solve a problem from the combinational subsystems point of view. We are going to use as many combinational blocks as we can using the standard blocks we have seen in the unit. So our problem is that we have data that comes in a line in groups of 7 bits, and it comes from some old equipment, an old teletype, and these are 7-bit ASCII characters. Now we want to use that data in a more modern system, in a computer or something like that, but our input, the input to our system, only uses 8-bit words. Okay, and those bits also are supposed to have some given parity. So what we need to do is to build this adaptation block where we take the teletype data as input, these 7 bits, and we generate a data output which is just these 7 bits, but with one additional bit. The additional bit makes this data to have even parity. Okay, so we basically only have to add 1 bit to the input data. Okay, this is in part A of the exercise. So we have to think on blocks we have already seen, and actually in the unit we have seen the how to build a parity detector. Basically, the exclusive OR operation is the means to detect parity. Okay, so if you combine several signals through a cascade of XOR operations like this, I'm calculating the parity of these two signals together. If I add an exclusive OR, then I calculate the parity of the 3 signals together, and so on. So basically, all we have to do is to use exclusive OR gates, and the output will it works as a detector in the sense that if P is equal to 1, it means that the parity of the bits operated is odd parity. Okay, but this value is also can be seen as a parity generator, because the odd parity generated here, if I combine to the original word, will make the parity to be even. Because if we have an odd number of ones and I add a 1 to that word, then the number of ones will become even. Okay, so the idea, once we know we can build a block which is a parity generator, will be to use our input. Okay, take our TT in input, put it into a parity detector or generator. If you call it detector or generator, it only depends on the point of view. Okay, this is a parity detector or generator, so you may see it. These are the 7 bits of my input, and it will generate that parity. Okay, this signal will be 1 when parity is odd. It will be 0 when parity is even. So how do I get my output, my P data that I need? So my P data is basically the same bits I have in the input. So I connect it to the output. Okay, but we add this bit here. So as I said before, if I have a set of bits with odd parity, and I have a 1 here when the parity is odd, if I combine that bit with the original ones. Then I have an odd number plus one additional one, so I will always have an even number of ones. Okay. So note that I'm using this bus notation. It means 7 bits of the signal TT in. This is the 8 bits of signal P data. Okay, and it doesn't mean that I make a connection of the signal. It's that I combine individual signals into more signals. Okay, so this is actually P data. P data bits that go from 6 to 0, and this is P data bit number 7. All together form the 8-bit of signal P data. Okay? This bus notation is very convenient because the alternative will have to draw all the lines. So let's for you to say it will be something like I have the TT in multi-bit signal. This signal could be 1, 2, 3, 4, 5, 7 bits. Okay, TT in number 6, 5, 4, 3, 5, 3, 6, 5, 4, 3, 2, 1, and 0. Okay, and then this connection, I will have to connect all these lines. Okay, like this one, this one, this one, this line here, this line here. It's going to be a bit messy, and the remaining line here. And I just say, when I put this symbol here, it means that I take this signal and just put together with this. Okay, and all this makes P data. This is what we mean when we use this notation. Okay? But when all these signals are really bits of a multi-bit, well identified multi-bit signal, then we always prefer this notation. Okay. So let's make it a bit smaller and leave it here as a side note. So this basically solves part A of my exercise. Okay, simply I take the input signal, calculate the parity, and combine the parity with the original set of signals. That's it. Now, I'd like to talk a bit more about this parity generator. If in fact we see that our parity generator is a connection of exclusive OR gates in cascade. Okay, but it's actually something like I connect. It's like when I have A and B, okay, and then I combine that result with an additional signal C, and so on. Okay, but can we use this is an exclusive OR. Okay, we use this notation instead? I may use simply this is an exclusive OR with 3 inputs. Okay, will this be equivalent to that? Okay, so actually to do that we must specify what it really mean, because if we write A, B, C, then it's not clear, it's not defined. What do I operate first? If A XOR B, the result is XORed with C, or maybe I operate B XOR C and the other way around. Okay, I can say that if I know that the order doesn't matter. So basically what I need to know if the XOR operation, seen as an operation, is fulfills the associative property. Okay, if it is the same to do the XOR of A and B and then XOR it with C, if it's the same, then XORing B and C and the result to be XORed with A. So is that true? When it's true, I can simply write these expressions as A XOR B XOR C, because order does not matter. The same thing we do with the or with the and. They fulfill the associativity property, the commutative property, so we can write a sum of terms or a product of sums, and we don't really need to specify the order because the order doesn't matter. But does it matter, the order with the XOR gates? Okay, so based on the definition, you know that X XOR Y is X complemented Y plus X Y complemented. If you apply the definition, you can demonstrate, it's not really difficult to demonstrate, that this is actually true. Okay, so we can write it like that. So it means I can simplify it like that. I can say I have an XOR gate with 3 inputs. It doesn't matter if in reality you will implement that XOR gate with this structure, with the other structure, or in any different way. Okay, so the XOR of many variables at the same time is well defined. You can do it in the order you prefer. For example, you could do something like, if you have to do the XOR of 4 signals, A, B, C, D, you could write something like this. Okay, and it can be done like here. A, B, C, D, and the result be XORed together with like this. Okay, or it could be done using a cascade structure. A, B, then we add C, and then we add B here. Okay, so but no matter how you actually implement it or what do you do in your circuit, you can talk about an XOR of multiple inputs, because it doesn't matter the order in which you operate these inputs. Okay, these variables. So actually we could draw our circuit like this, but this parity detector or generator is no more than a multi-bit XOR gate. So we could have drawn our circuit like I have TT in. The 7-bit input goes to an XOR gate. It's not an input, it's just 7 inputs. Okay, this is our parity bit, so it goes to the output. Okay, to P data, together with the rest of the bits here. Okay, it is bit 7 in P data, and these are bits 6 to 0 of P data. Okay. We can make a more compact representation like this. Okay, now let's again make it this. Let's screen up a little bit. And let's make it a bit smaller. Let's put it over here. I have to try to do it a bit smaller in the first place. Okay, because I want to keep the full solution in a single page. Okay, now it's case B. We need to add a control signal because now I want my system to be able to work when the output goes to a system that accepts even parity data or odd parity data. Normally, serial ports can be configured to work in even mode or in odd mode. Okay, so we want to add a control signal. So when P is 0, it behaves just like in part A. It will generate an even word, but when P is 1, I want it to generate an odd word. Okay, so the result is actually very similar. We can start with the previous design that we had here. I'm actually I'm going to copy it. Keep it smaller here. Okay, great. Let me make some variations. Okay, great. Now, we will start with the previous design and modify it a little bit. So now we want it to work like this, but now we generate this bit is 1 when the parity is odd. Okay, so the idea is if we want my data to have odd parity, I'm not interested in adding this bit, to add a 1 when the parity is odd, because we want the parity to be odd, to keep being odd. Okay, so when parity is already odd, I want to add a 0. When parity is even, then is when I want to add a 1. Okay, so I actually am interested in adding the complement of this bit that I had before. Okay, that a solution will be to simply complement that. Okay, I include an inverter here. So now I will have a circuit that makes a data with odd parity instead of even parity. If the parity is odd, it will generate a 1. A 1 becomes a 0. A 0 combined with something with odd parity will remain being odd. Okay. If parity is even, it will generate a 0 here. This 0 will become a 1, and even parity combined with a 1 will give odd parity again. So the problem is that we want a direct connection when P is equal to 0, okay, but we want to have an inverter when P is equal to 1. Okay, if we think in the problem from the point of view of the subsystems we have seen in the unit, this is like a selector. I want to select just the output of this circuit when P is 0, or I want to select the complement of the output when P is 1. And selection means multiplexers. Okay, so the idea is very simple. We can add a multiplexer here here, for example, and what we do is that we will control the multiplexer with my control signal P, and then we will say this is 0 and 1. When P is equal to 0, I want my parity to be even, so I take directly the output from my block as we did in the first part of the exercise. But when the P is 1, I don't want the 0, I want like the complement. So when P is 1, I will select this channel of the multiplexer, and I want that channel to be the complement. Okay. So that's it. So that would solve my problem. Now it can be configured. I take the original output or I take the complement depending on P. Okay. So that's how we solve problems with this block thinking. Okay. We think of the functionality we want, and then we find the block that does that functionality. Okay, great. But now consider this another option that will be a correct solution. This is perfect. Okay. But there's another option. Consider our parity detector here. Okay. Our parity detector detects the parity of these 7 bits. But this is simply, and I said, it's simply a set of exclusive OR gates. So I will recover the original, the previous alternative. Okay, we mentioned take this alternative. Okay, let's make this copy a bit bigger. Now, but this exclusive OR gate here will generate the parity bit, which is the parity of these 7 bits. Okay. If you remember from the unit, the exclusive OR gate is like a transfer complement block. Okay, basically it's if I have a exclusive OR, I have input X here, the other input I consider it to be a control signal, okay, and have Y here. What happened here is that if P is equal to 0, okay, if P is 0, Y is equal to X, because the exclusive OR with a 0 makes the same value, okay? But if P is equal to 1, X will be equal to Y, sorry, will be equal to X complemented, okay? So by using one of the inputs of the exclusive OR gate, we can make the exclusive OR to generate the same value or to generate the complement of the value inside that. Okay, we can do something similar here. What happens if we add our control signal P to this exclusive OR? We make it a 7 + 1, 8 input exclusive OR. So it happens when P is equal to 0, nothing changes. Okay, the exclusive OR will be 1 when there's an odd number of 1 bits in the input. Okay, because P is equal to 0, it doesn't alter the parity of the input. Okay, so we have exactly the same result we had before. But when P is 1, this exclusive OR is a parity detector. When the parity is even, this will make the parity to be odd, and we have a 1 here. Okay, even parity and a 1 will make odd parity at the output. Okay, so even parity will be converted to odd parity. But if we have odd parity here, an additional 1 will make the parity even. Even will give a 0 here, and the 0 will not change the parity. So even parity here or odd parity here will not be changed here. So we'll get odd parity all the time. So this could be also an alternative design for my problem, using the properties of the exclusive OR gate. Just add one additional input to the gate, okay, instead of using a multiplexer. So now a final note is, you may think that, or one may think that this solution is better, because you may think that the exclusive OR is just a gate. Adding one additional input to a gate may not be very difficult, okay? It must be something simple, more simple than using a multiplexer and an inverter. But we cannot be sure if we don't actually know the implementation, because exclusive OR gates are not easy to implement. Remember that the exclusive OR operation, x or y, here, here, x or y is x complemented y plus x y complemented. Exclusive OR operations are really expensive. It means making two complements, okay, and two AND operations and an OR operation, okay. Remember that a multiplexer, the two inputs multiplexer, is not a very difficult circuit. Actually, it's very similar to this, okay. The two input multiplexer is this one with some additional signals here. So it may happen that the actual implementation of these two circuits is not that different in reality, but anyway, I think this solution is quite smart, and that's it. This is the idea. When we think, instead of thinking on the truth table of my function and do it with a generic system like the kernel map minimization, here, once we understand the functionality of devices like parity generators, multiplexers, like the properties of the exclusive OR gates as a module, we can combine all those functionality to find a solution for a problem. And it doesn't really matter which is the number of bits. It's important to know that the same problem we can solve with any number of bits. The number of bits here, these 7 bits, it's a typical example for a circuit that uses that encodes characters. But we may have had more bits, 32 bits, 64 bits, and this solution is exactly the same. It only changes how many bits do I need to put here. Okay, so that's it. Thank you.